plan on this is to do wavelet theory, but in order to get started, I'm going to talk about Gabor systems and wavelet systems simultaneously, or kind of simultaneously, at the same time period. And then by next week, we will leave the Gabor theory to the side a little bit and just concentrate on the wavelet theory. But there are similarities and real differences between the two theories that I want to point out initially. Gabor was this, let's say, genius, the Nobel Prize in the early 70s for essentially discovering lasers and other things like that. But of course, when he made the discovery, it was in the 40s, where you couldn't build anything like that. So it was one of those remarkable mental developments. So, John, so the definition, the Gabor, or Dale Heisenberg, there's a lot of fancy names in this definition. System of coherent states is the sequence double sequence G, M, N, where M and N are in Z cross. Oh, excuse me, I should have, sorry. Let's just take, let G be an element in L2 of R. And I'm only going to do this on R now, but everything I'm saying is going to be much more general. And let A and B be positive numbers. Okay. So the Gabor system is this sequence GMN defined as G M N of T.
He's white out.
Oh.
Sorry, it's white noise.
E to the 2 pi I. If you're going to use it with my lecture, you should bring it in by the gallon. I mean, it's e to the 2 pi I T M B G of T minus N A. And the notation we've talked about earlier tonight, this is really just an exponential E M B at T times the translation tau N A G. Right? So what it is a translation and a modulation, and so it's really putting together two of the fundamental invariants, quasi-invariants, because translation goes into modulation, and modulation goes into translation of Fourier analysis. And an easy calculation is the note G M N hat at gamma. You can see what it's going to come out to be is equal to the translation by MB of the modulation e to the minus N A G hat at gamma. I'm not going to do that calculation out, but it should be fun for you to try to do that, okay? Well, you can compute that Fourier transform. Okay, now, typically one uses for wavelets the Greek letter psi. So definition, let psi be in L2 of R. The dyadic wavelet for affine system the psi is the sequence psi mn, where m and n are in Z cross Z, defined as follows, where psi m n of t is equal to 2 to the m over 2 for normalization purposes, psi of 2 to the m t minus m. And again, it's easy to compute the Fourier transform of that, so clearly psi mn hat of gamma is equal to 2 to the minus m over 2, and then E minus n psi hat evaluated at gamma over 2 to the n. And I'm not going to write out the details, I've done it about a zillion times in my life, but you should to see what's going on. You sort of know that's what's going to happen. But you don't know exactly what it would be just looking at it. But you know, since you have a translation, you're going to pick up a modulation. Since you have a dilation, that's going to turn into a dilation. And because of the uncertainty principle, the dilations in one direction go into dilations in other directions. And so if there was a lot of pressure on you and you just had to guess without actually doing the precise details, you'd come close to this. This is correct. Now, I'm not going to try to wax eloquent about all of the subtleties involved here, but because, or another term for that is BS. But what's going on here, I do want to mention it briefly. What's going on here is there's a very famous group called the Heisenberg group. And the Heisenberg group is really behind the Gauss system. And there's another group called the AX plus B, or affine group, and that's really behind Wavelet theory. They're both relatively elementary, non-abelian groups. And it may come as no surprise to you that people have combined them to look at combinations where you have translations, dilations, and modulations all together. Something called metaplectic group situation. And some of my students, by the way, years ago, some of the people who did this theory first, and my colleague, Wojtek Shaya, is also the world authority in this area, when you combine things. I'm not going to do that in this course. And this is an elementary course. I want to establish the theory very basically. If there are people interested to have courses like that, I'm very happy to offer them. I want to say one remark about the Gabor theory vis-a-vis Gabor. The history of this is there was this wonderful book which is still very interesting to read by von Neumann. Back in the late 20s he wrote it, and it's had many reprints throughout the years. And it's basically quantum mechanics and which has a lot of Hilbert space theory in it. It's a very modern approach to quantum mechanics, especially since when it was written. And he does these expansions in terms of, he expands series, he expands signals in terms of modulates and translates. And a lot of the theoretical physics community, especially in the late 60s, early 70s, wrote papers about these coherent states and how they're complete in certain spaces of signals. Gabor was a physicist and a great engineer, and he wrote a paper right after World War II on acoustics, which is when he did his Gabor theory. And like many geniuses, every step he made a technical mistake, but he knew how to get across the street. I say that with great respect for this person. Because he did these expansions, and basically they didn't converge. He didn't know the Heisenberg group from a group of geese, even though I know it's a guy. But he did the laser business right around the same time. And I've always, wondered what was in his brain. He obviously had a spectacular brain. Did he somehow understand, because basically people have understood since then that some of the laser theory can be formulated in terms of the Heisenberg group. And in the laser theory he did, there was no mention of any of this Heisenberg group, so he didn't know what it was, or of this type of thing. But somehow or another they're related, and he did it all right after World War II. So it's sort of something miraculous intellectually that I'm just telling you about now. In any case, we are going to be interested in, for a given function, writing down that function as an infinite sum of functions like this with coefficients, or functions like this with coefficients. For example, in this case, that's a Wavelet decomposition. There are real reasons for doing that that are fascinating to me, and to a lot of other people, I must say. And we're going to, that's in some sense the thrust of the first half of this course, to see how to do that effectively, and to see what that really means. Okay? Now, there are many, many books on Wavelet theory, which is why I'm never going to publish anything like this. Basically, there's a book a week that's coming out in the 90s. But there are three great books, and many very good ones. And maybe there are more than three great books. There are three great books that I know, since I'm on film now. I have to be careful. But oh, by the way, someone asked about literature. Nate is also getting a list of books from me, and he's going to put this on the as part of the PDF file with the exercises. So at some point in the next week or so, you're going to get more exercises plus an ever-expanding list of books on the subject. Okay? But the three of the main books on the subject by Yves Meyer, Les Ondelets, that's Wavelet. I'm sorry?
Is it in French?
Yes.
Okay.
No, but there is, I could really sound pompous and say, yes, of course. But if you don't read French, there's an English translation of at least one of them. But there are three French volumes. There are lots of books, but you can get an English translation also. Then there's Ingrid Daubechi's book, which is modestly called 10 Lectures in Wavelets. But you can just imagine what those lectures were like if you look at the book. It's a great book. All three of these books. And then there's Stéphane Malat's book, And that's a, I don't know, journey through signal processing.
A Wavelet tour of signal processing.
Thank you. I reviewed the book, I just forgot the title. And I would say this book is really for mathematicians. This book is for applied mathematicians. I shouldn't distinguish because I can't distinguish myself between the two concepts. So maybe we should cut this from the film. And this book is for applied mathematicians and engineers. So, maybe that's a better way of putting it. This is for mathematicians, applied mathematicians. And there's no question this is really, it's a very, very mathematical. Yeah, they are wonderful books. They were all written quite a while ago. Ingrid's book was published in '92, and Eve's book was published in '90, and Black's book was mid-'90s, I guess, I forgot exactly. And they are still very, very relevant. Okay. Now, what I'm going to do is, I want to, just like I told you a little bit of the history of the Russell summation formula, I want to tell you a little bit of the history of wavelets. I mean, basically, this is what we're going to do. I mean, we are going to look at signals, and we're going to expand them like this, or like this, and I'm going to tell you why there are good reasons to do both. And by the way, why sometimes any other expansion could be better. There's nothing sacred about either of these. I mean, sometimes one is good, sometimes the other is good, and sometimes neither is better than other existing techniques. I must say, because of my age, I've been around this business for a long time, and I have the advantage of never having made a contribution to the field. So this is actually a plus in some sense, at least in the fundamental theory. So I've actually written a history of the subject because of that. As I say, I'm definitely not touting my work in this course, but there's a wonderful book out that was edited by Highland Walnut, both of the PhDs here with me, and it's Kyle and Walnut. And Walden has also written a very good Wavelet book. And basically, they're editors of it. And it's called Fundamental Papers in Wavelet Theory. And I would say that they did a marvelous job of putting together the fundamental papers of Wavelet theory. And it's a Princeton publication, Princeton University publication. And anyhow, I wrote the introduction to it, and I took that opportunity to write essentially the history of it as I understood it at the outset. So I recommend the book in general, but if you're interested in the history of the subject, it might be amusing to read. Okay, but in a nutshell, let me give you the history. So we are going to take the point of view of decompositions, history, from point of view of signal decompositions. And, well, from a very mathematical point of view, for those of you taking real variables or maybe baby functional analysis, you think in terms of there are bases. Okay, there are Hamel bases, There are shadow bases. There are lots of bases. Orthonormal bases. Da, 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 da. So those are ways of decomposing things. Well, another way of decomposing things is Fourier series on transforms. Splines. I just had a senior moment, but one of the great spliners of the world has passed away. I can't think of his name. He's a Swedish mathematician. But when I was first getting involved in wavelet theory, I went to Chicago, and Eve was there giving the Zignum lectures on wavelet theory. And this fellow was also there. And one night, we were actually top of this Hancock Tower, I think it's called that, very tall building in Chicago. There we go. It is the Hancock.
There's the CS Tower also.
Oh. Anyhow, we were drinking Bombay gin. I forgot the tower was in, but anyhow, Ingrid had just called, and she had just proved her big theorem, which I'll tell you about in just a moment. Eve had given lectures on basically MRA, but it was just getting started. This is 1987. And this fellow, X, really embarrassing, I can't remember his name. Two things I remember about him from that evening, though. He was a consultant for the Volvo Corporation because they hired him for design features for the Volvo because of his knowledge of splines. Now, Volvos for that era were not in the Lamborghini class, I would say, as far as beauty went, but apparently their spline properties were very good. But the other thing I remember was we were looking over the city from this high place, and he said, "Look out there, John, isn't it beautiful?" I said, "Yeah, it's beautiful." He said, "There's nothing like that in College Park, is there?" So I'll leave you speechless, but anyhow. Later, in the direction of wavelets, there were three developments. There was Haar, who wrote his thesis in 1909 and 1910. And by the way, one of my former students, Zimmerman, translated it, and of course it's in this book. It's a remarkable paper, a long time ago, 1909, in the real wavelets. And then the next development was by Franklin, who was a professor at MIT in the 20s. About 27. And one of his other claims to fame, he was Norbert Wiener's brother-in-law. And then Jan Olof Stromberg, and that's probably in the 70s. And these were directly related to wavelets. So, another force that came through here, which was very, very sophisticated, difficult classical harmonic analysis, being developed by Paley and Littlewood in the 30s. And that, in some very real sense, was wavelet theory. So the Littlewood-Paley theory and a sequel to that was the Calderon form. So these things here are mathematical and definitely wavelet oriented. Then, from the physics point of view, is what I just said. By the way, I make no apologies for this, even though I'm not beating you up with a lot of technical stuff. I believe this background is very important. So, So this is for mathematics. And from physics, there was the von Neumann's book that I mentioned. And the sequel to that, and the Heisenberg group and Vail, and et cetera. I won't write all those things down since it's a deep word. And then in engineering, for years, people have been doing, so this was more associated with the Gabel theory, what we call it Vail, Heisenberg, or Gabel. And it was really being done in physics theory. And then in engineering, there was the short time Fourier transform. And here, basically, in fact, people still do it. I mean, it's like the first line of offense when you want to understand something physically, is to take a short time Fourier transform. You can give a spectrogram to read. You're not getting any phase data, but it's very interesting to try to read a spectrogram. There are guys and women who read these things. It's sort of amazing about the phase there. But in general, you really would like to have some phase there. But that's also related to the Gabel theory, and a staple in engineering for many years. And also in that realm, there was a lot of work done in the area of speech. And the speech processing certainly dealt with that. The speech processing also dealt with wavelets. And this goes back to the 1970s. When people introduced the idea of quadrature mirror filters, or Milan calls them conjugate mirror filters, but anyhow, quadratic mirror filters. But then, around the same time, but in the early 80s, I'm just going to put a number here because I know one of the fundamental papers was then, as opposed to 1989. From image processing. With these pyramidal schemes. And together, these two ideas really led to MRAs. But the speech people really weren't dealing with the image people, or vice versa, or talking to the mathematicians or the physicists. These were all sort of incredibly brilliant, independent contributions. And then another aspect, which maybe many of you have heard about this, well, there's radar, the ambiguity function. Radar, narrowband radar ambiguity function due to Woodward in the early 50s. His famous book was in 53. And that is somehow a special case of the short time Fourier transform. And then there were the Walsh functions. And the Walsh functions are due to Joe Walsh, who was a professor here after his retirement from Harvard. And he taught me potential theory at Harvard. And when we arrived here the same year, 65, and at that time, he said, John, he said, you should look at these, I forgot if you call them Walsh functions or not, and NRL was supporting a lot of that research in them. But I didn't take advice from people, I guess. I didn't take his advice in any case. But on that matter, very, very nice guy. I just didn't obey him. But these Walsh functions, which emanated from the Haar theory, are really primordial case of wavelet packets, which is the most sophisticated form of wavelet theory. And we're going to do that. That will be done. So these are wavelet packets. And maybe I'll stop writing now, but somehow all these things were going on independently. And what broke it all open was usually oil is a bad thing as far as morality and wars and things like that goes. But oil had something to do with this because the French were trying to find oil in the Sahara, and there was a great geophysicist they had by the name of Morley who had these ideas. And it turns out his ideas as a geophysicist were very, very closely related to doing this. And he had some physics friends, in particular Alex Grossman. And he asked Grossman some of the math questions associated with it. And Grossman said, well, you know, Grossman was really pretty smart. He said, let me ask my good friend Yves Mayer. And I think Ingrid was a postdoc with Grossman's at the time. And somehow the rest is history. I mean, basically, these people finally got together at that level. And then within a few years, I was fortunate enough to go to Wright-Patterson Air Force Base for about 20 of us there, where people from all of these communities were getting together. This was a long time ago, early 90s. And people were just then really realizing that all these things were equivalent. So that's a story which happens to be true. Besides the French connection with Mayer and Grossman, who's actually Hungarian, who's in France, wavelets also emerged independently, I would say, in a couple of other places. One was Austria, where Birkenig and Feichting and Birkenig developed it as part of a very general theory of harmonic analysis. It was so general, a lot of people didn't read their papers at the time. They did it contemporaneously with the Mayer effort. And the other was here in the United States, where Yaworth and Mike Fraser did it as a continuation of their work on the Lulu Paley theory. So that's what I'm going to say about this. Now, let me say a little bit about the. So that's the talk. Now let me do a calculation, which is the Calderon formula, because it really gives us a hint of how to make expansions like this, or, you know, why it might be amusing. So let's start over here. So Alberto Calderon is an Argentinian who was really one of the great harmonica analysts of the 20th century. A very, very deep mathematician. And so what I'm about to say is not something he's really known for as far as his depth goes, but it is a wavelet decomposition. And the formula is the following. F of t equals the integral from 0 to infinity psi 1 over u, convolution, remember we defined that last time, psi 1 over u, convolution f at t du over u. And basically the formula says something like this. There exists psi such that for every f in L2 of R, we have that formula. Now what does that have to do with what I'm talking about writing out signal decompositions? Well, let's write this out. So the right-hand side let's see what I mean. The right-hand side of 1 here. If I just, yeah.
So I'm just trying to figure what this is. The first subscript is 1 over u, and this.
That's a 1 over u and a 1 over u.
Oh,
And everything else?
yeah.
So let's write what that is, just to see what it is. Well, that's equal to the integral from 0 to infinity of the integral. I'm going to write out these convolutions, as boring as that might seem, of the integral over the whole real line in this case, of psi 1 over u v minus w f of w dw. Okay, that's that convolution there, and now I'm getting it as a function of the v, right? And now I'm integrating here to get the remaining part of the convolution, and so I have there psi 1 over u of v minus t. And now I've got a dv, so this is all dv du over, okay, you can impress your beloved with this, but
T minus B.
uh,
Not that it really matters, that.
well, I'm going to have even functions, so in fact it doesn't matter,
Okay.
but you're absolutely right. Let's leave it this way since I'm going to do evens. And what this really is the following. This is the integral of 0 to infinity of the integral dot 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 let's see how I want to make my point here, of these guys times this guy times my measure. So drop that in here, and drop that in here, and then I'm going to have this dv du over u. So the point is, I'm writing out any function f as this double sum of these coefficients, where I'm pointing is rather relevant, times this function here. And this function here, I'm summing over all the v's and the u's to get a value at f of t. That's exactly what I mean when I talk about a wavelet decomposition. When we talk about a wavelet decomposition, we're going to have something like f is equal to the sum of the inner products like this. Where I have m. I'm just saying to you that that, in a integral sense, is this. Right? Now, for those of you who have studied a little bit of functional analysis, you know about orthonormal bases, and you know about orthonormal bases in other ways too, in linear algebra. But if these were orthonormal bases, then that's what f is, right? You write down f that way. Well, these wavelets we have, that's what they'll be initially. They'll be orthonormal bases, and it's just that instead of sort of well-known classical ones that might not have physical meaning, our wavelet orthonormal bases are going to have this form, and they really will have physical meaning. What the Calderon formula is as a calculus version of that, in the sense of the real line, etc. And of course, it also gives great flexibility because it's true for a huge class of function psi. See, typically in the old days, people said, well, what's an orthonormal basis for L2 of R? Well, if you ask for an orthonormal basis of L2 of 0, 1, that's easy. Those exponentials will do it. But when you do the real line, then life becomes complicated. And there are functions that work. Okay, they're well-known functions that work, but not, somehow people didn't think there were that many of them. I don't want to trivialize it, but, and they certainly didn't look to them for their physical needs. Here, we're saying, gee, there are a lot of functions psi which this works. And this in some sense, inspired the idea of discretizing this in order to come up with this for lots of functions psi. That's the point I want. Okay, so one of the things I said, so this is a continuous wavelet transform. And what I say here is that there are functions psi for which this holds. Yes, sir.
I was just wondering if there's an intuitive explanation where the 1 over u comes into play.
Well, yeah, I like to think of it as a hyperbolic measure. Basically, it's the higher measure that you're going to get when you talk about this AX plus B group. So it's intuitive. That may not be intuitive, but that's one of the driving forces. Okay, so let's see how one would. I mean, I'm telling you there's a psi. Let me see if I can convince you more by just being curious that there is a psi. Well, let's just look at that formula and take its Fourier transform. So, the Fourier transform, so to see what psi must satisfy. Fourier transform of 1 is f hat of gamma is equal to, well, we know how to take Fourier transforms of convolutions. We did that last time, remember? And just the product of the Fourier transforms. And so this is equal to, when you take the Fourier transform in here, I get a 1 over u. So that the Fourier transform of that is going to go into a u times the psi hat. I get 3 of those babies, and it's the u that's the variable. So I'm going to be able to pull out at f hat of gamma. So I'm going to take the Fourier transform with the variable being gamma. This is really equal to, so the left-hand side, this is the left-hand side, and the right-hand side is f hat of gamma times the integral from 0 to 1 psi hat u gamma squared du. So now the question is, can we find, does there exist a psi such that this integral here from 0 to 1, 0 to, that's obviously wrong, the whole real line. But now, because of the 0 to infinity, 0 to infinity, psi hat u gamma du over u is equal to 1. Okay.
You say I was squared?
I want to square it, yeah. Is equal to 1 for all gamma not equal to 0. I mean, I only needed all this everywhere. When gamma is equal to 0, things are good. Okay, so that's a meaningful question. And we would not even be having this discussion unless the answer was yes. So question. And the answer, yes. And basically, this is written down in a number of places, but I worked out all the details in my harmonic analysis book. And let's see if I gave a reference here. So that's a C example 2.2.2C. Now, there's a wonderful book on this subject that's due to, it'll be on your list, so I'm not going to write it out right now. That's due to Fraser again, who's a co-author of mine too, a wonderful guy. Weiss, who's one of our senior members of the harmonic analysis community, and Yauer. So they wrote a book together, basically on the Calderon theory of the movement theory. And you see this type of development done very extensively, more or less completely. In any case, there are lots of size this holds. And so basically, the continuous wavelet transform theory shows that there are lots of these wavelet psi play the game. And now you want to discretize, because after all, when you can do this, you can put a computer, you can compute with it, and the answer is also yes. There are lots of these babies. How's my time? We'll go another 10 minutes or so. Let me draw one picture, show you one possible reason for looking at this type of function. If I take the following function, let's take the function defined on 0 to 1, that's identically 1. And now let's look at it periodically. Let's look at the periodic extension. So I can talk about the Fourier series of that function. Well, the Fourier series of that function is rather elementary, because all the Fourier coefficients are 0 except for the 0th one, which is equal to 1. However, now let's say I look at the following function. Let's say I look at this function here. I'm taking liberties knowing that this is being recorded. Normally I'd be drawing all the pictures and writing all the formulas down. But what I'm saying is true. But now let's look at the same function, except not quite the same. And so it's going to be the same most of the time, but then I'm just going to do a little blip here. And then have this thing periodic. And take its Fourier series. Now what is true is that by certain measures, like in L2, the coefficients are going to be close to 0 in the non-zero case, but they're all going to be different. I mean, you might get some 0, but basically you can't look at those coefficients and say what the function is. Okay? And so you don't have any localization of coefficients in that sense. Now, let's say we do the same business but with a wavelet decomposition. And in that case, I'm going to look at the following wavelet. This really is the Haar wavelet, by the way. So the Haar wavelet, which had it back in 100 years ago, psi of t is equal to 1 and minus 1, 0, 1 half, and 1 half, 1, and 0 elsewhere. Now, we're going to be doing lots of calculations with this, and of course you probably want to do this calculation yourself but I'm not going to do the details right now. But I'm just going to say that notice, first of all, that the integral of each psi mn is equal to 0, where psi mn is defined this way, just by doing the calculation. Also notice that if I look at the mn term, depending on the size, if I'm looking at my function, let's say I'm looking at my function here, so that's the function I want to analyze. And I take n and m the right way, so that n, that point there, is n over 2 to the m. Then this psi mn is going to look this way. I mean, it depends on the size of m and m, but psi mn is going to look like this. So my function s here, what we called it, s, so psi mn is an orthonormal basis. That has to be proved. To be proved. But believe it for the moment. So therefore, S is equal to the sum of the inner products of S psi mn, psi mn. Right? But look, in this case, these guys will be 0 all the time. Okay? So if I do a little blip here, that'll be the one place it's not 0. And that's the amazing thing. So what that says is that if I just adjust my function just a little teeny bit, I am going to get 0 coefficients along the place, except I won't get a 0 coefficient when my test function psi mn hits this area. And that's one of the distinguishing features. Now, people sometimes, well, people have said, oh, that beats the uncertainty principle. Well, it doesn't beat the uncertainty principle, but if you want to have a situation where local behavior is reflected in a quantitative way, in the way I suggested by saying that Fourier analysis doesn't happen, then certainly Wavelet theory does. So that is one of the distinguishing features. And we're going to cover a number of other very important distinguishing features. Now, I said earlier the way Ingrid Daubechies proved this big theorem in 1987 when we were all in Chicago, and we heard the word. And let me just state it. Right. As I say, Meyer had already done significant work in this area, but this was a very significant theorem. And this was very significant. Because by this time, everyone knew that, see, Haar did his work on intervals like 0, 1. But everyone knew by this time that the Haar theory could be extended to R. Not obvious, but that it could be. But those functions are not continuous. What Daubechies proved is the following theorem. So let R be bigger than or equal to 1, then there exists a psi in which is R times continuously differentiable, and that has compact support. It's very relevant. So R times continuously differentiable compact support, such that psi mn is an orthonormal basis for L2 pi. And this, in some sense, was one of the great starting points of wavelet theory because of the getting continuous functions, smooth functions of fields. And I'll explain why that is interesting as time goes on. My voice is giving out. I didn't cover maybe as much technically as people who's paying your tuition would like to have seen tonight, but I think I still took a lot of information. But we will make up for it.